The edge of the observable universe holds secrets from the dawn of time. We are embarking on an epic journey to uncover 50 incredible facts about the most distant galaxies ever seen. By the end of this exploration, you will possess a new understanding of the universe's infancy and our own cosmic origins. We will investigate why some of these ancient galaxies appear impossibly bright and what mysterious forces shaped their chaotic forms. What single question about our cosmic beginnings would you most want answered? Our journey begins with a simple yet profound idea. When we call a galaxy distant, we are not just describing a vast physical separation. We are talking about a journey through time itself. Light, while incredibly fast, takes a measurable amount of time to travel across the cosmos. So when we observe a galaxy millions or even billions of light years away, we are not seeing it in its current state. We are receiving a snapshot of its ancient past, a delayed message from an era long gone. This is the concept of look-back time. The farther away a galaxy is, the further back in time we are looking. The most distant galaxies we can detect appear to us as they were when the universe was only a few 100 million years old, mere infants in cosmic terms. How do we even know how far back we are looking? The key lies in a phenomenon called redshift. As the universe expands, it stretches the very fabric of space. This stretching also extends the light waves traveling through it, shifting them toward the red end of the electromagnetic spectrum. Think of the sound of a siren on a passing car. As the car moves away from you, the sound waves stretch out and the pitch drops. Light from receding galaxies behaves in a similar way. The greater the redshift, the faster the galaxy is moving away from us, and therefore, the farther away and more ancient it is. So that faint red smudge in a telescope image is not just a distant object. It is a fossilized echo, a direct glimpse into the universe's fiery and formative youth. What could these ancient messengers possibly tell us about our own cosmic roots? That faint red smudge holds a name, GNZ 11, and it currently holds the title of the most distant galaxy humanity has ever confirmed. We see this galaxy not as it is today, but as it existed a staggering 13.4 billion years ago. This means the light now reaching our telescopes began its journey when the universe was a mere 400 million years old. To put that into perspective, the universe was only about 3% of its current age. GNZ 11 is not just distant, it is profoundly ancient. Its incredible distance is measured by its redshift, a value of 11.1. This high number tells astronomers that the expansion of the universe has stretched its light dramatically, shifting it far into the infrared part of the spectrum. What is truly baffling about this record holder is its unexpected nature. For a galaxy so young in cosmic terms, it is surprisingly bright and massive. It churns out new stars at a rate much higher than our own Milky Way does today. How could such a mature, vibrant galaxy have assembled itself so quickly after the Big Bang? Its compact size, only about 1/25th the size of our galaxy, yet with a brilliant core of stellar activity, challenges our theories of how the first structures in the universe formed. This ancient beacon forces us to reconsider the very timeline of cosmic evolution. How do we actually measure a distance so vast it spans billions of years? The primary tool astronomers use is called spectroscopic redshift. It is far more precise than just noting a galaxy looks red in an image. This method involves dissecting the light from a galaxy, spreading it out into a full rainbow spectrum, and searching for telltale dark lines. These lines are like cosmic fingerprints, created when specific elements in the galaxy, like hydrogen or oxygen, absorb very particular colors of light. We know exactly what patterns these fingerprints should have if the galaxy were stationary, but in a universe that is expanding, those patterns are never where we expect them to be. The fingerprints are all shifted toward the red end of the spectrum. The more stretched the light, the greater the redshift, and the faster the galaxy is receding from us. This shift is not just a measure of speed, it is our direct window into cosmic distances. Because the universe expands at a known and accelerating rate, we can take that redshift value, plug it into our equations, and calculate exactly how far away the galaxy is. And since light takes time to travel, that distance also tells us the galaxy's age, revealing precisely how far back in time we are peering. A single stretched wave of light carries a message of both space and time, a dual revelation from the edge of our vision. Capturing these ancient whispers of light required a new kind of eye, one placed high above our shimmering atmosphere. The Hubble Space Telescope became that eye, and its greatest triumph was not just seeing farther, but seeing deeper in time. Before Hubble, the spaces between bright, nearby galaxies appeared as empty, black voids. Astronomers dared to ask a simple, radical question. What if that blackness was not empty at all, but simply unseen? To find out, they pointed Hubble at a seemingly barren patch of sky, a region no larger than a grain of sand held at arm's length, and let it stare. It stared for 10 consecutive days, gathering every single photon of light it could. The result was the Hubble Deep Field, an image that forever changed our place in the cosmos. That tiny, dark speck of space was not empty. It was crammed with thousands of galaxies, each a faint smudge of ancient light. Every spot, every swirl, was an entire galaxy, some so distant we were seeing them just 1 billion years after the Big Bang. This was not a simple photograph. It was a core sample of the universe, a deep drill into the history of everything. Later, the Hubble Ultra Deep Field pushed even further, staring for 1 million seconds to reveal galaxies from the cosmic dark ages, the very first cities of stars. These images transformed our understanding from a universe sparsely populated to one overwhelmingly rich with galaxies, a tapestry of countless island universes stretching back to the dawn of time. What other secrets lie hidden in the darkness between the stars? Yet even Hubble had its limits, a horizon beyond which it could not see. The universe's relentless expansion had stretched the light from the very first galaxies so extremely that it had passed from visible light into the infrared spectrum, a realm invisible to Hubble's eyes. This is where a new champion enters the story, the James Webb Space Telescope. Designed as Hubble's powerful successor, Webb is not just an upgrade, it is a completely new kind of observatory. Its primary mission is to see the unseeable, to peer into that cosmic infancy where Hubble's vision faded. Its giant golden mirror, over 6 times larger than Hubble's light-collecting area, acts as a colossal ear cupped toward the cosmos, straining to hear the faintest whispers from the dawn of time. But its true superpower is its specialization in infrared light. Because the expanding universe stretches ancient light into long, red waves, Webb is perfectly tuned to catch these signals. It sees the heat glow of creation itself. Furthermore, infrared vision allows Webb to peer through vast clouds of cosmic dust that would completely block Hubble's view. These dusty nebulae are the very nurseries where stars and planets are born, meaning Webb can watch the construction of the first galaxies in real time, or rather, in deeply ancient time. It is like moving from a standard camera to one with night vision and X-ray capabilities, suddenly revealing a hidden universe bustling with activity where we once saw only empty space. What will this new eye find when it stares into the absolute darkness before the first stars switched on? This era of first light is known as the cosmic dawn, a period of profound transformation that ended the universe's long, silent night. For hundreds of millions of years after the Big Bang, the cosmos was a dark, featureless sea of hydrogen and helium gas. There were no stars, no galaxies, and no sources of light. This was the cosmic dark ages. The cosmic dawn marked the moment this profound darkness began to recede, as the very first stars and galaxies flickered into existence. Their faint collective glow began to burn away the primordial fog, a process astronomers call reionization. These first objects were not like the stars we see today. Theorists believe they were behemoths, monsters made of pure primordial gas, burning ferociously bright and dying young in colossal supernova explosions. They forged the first heavy elements, the very building blocks for future planets and life itself, and seeded them across the young cosmos. The most distant galaxies we are now discovering, like GNZ 11, are the direct descendants of those first pioneers. By studying them, we are effectively watching the end of the Dark Ages and witnessing the universe turn on the lights for the very first time. What did that first sunrise in the cosmos actually look like, and how did its faint glow manage to illuminate the entirety of existence? These brilliant infant galaxies defied every expectation. When the James Webb Space Telescope first opened its infrared eyes, it immediately began finding galaxies from the cosmic dawn that were shockingly luminous and fully formed. Our best models had predicted a young universe populated by small, faint, and chaotic collections of the first stars. Instead, Webb revealed cosmic toddlers that were already giants, shining with a maturity that seemed to belong to a much older universe. This was not just one oddball galaxy, but a whole population of them, appearing far too bright and massive for their age. How could such vast structures, some containing billions of stars, have assembled themselves in what amounts to a cosmic blink of an eye? This single observation sent shockwaves through the world of astronomy, forcing a fundamental re-examination of our theories about galaxy formation. The timeline we had so carefully constructed now appears too slow, too cautious. It seems the early universe worked with a startling efficiency, building galactic cities at a breakneck pace that we are only beginning to comprehend. Did some unknown physical process, now dormant, accelerate the birth of stars in that primordial era? Or are we witnessing the effects of stars themselves being fundamentally different? Perhaps those first monster stars burning with an intensity we can barely fathom. The sheer brightness of these ancient beacons is a direct challenge, a cosmic puzzle that whispers of forgotten laws from the universe's first breaths. The chaotic forms of these infant galaxies reveal a universe still learning its own rules. Unlike the majestic, well-ordered spirals and smooth ellipticals that dominate our modern cosmic neighborhood, the most distant galaxies are often bizarre and misshapen. They appear as ragged blobs, tangled chains, or lopsided clumps of light, with no central bulge or sweeping arms. This is because the early universe was a far more violent and crowded place. Galaxies were constantly colliding and merging, their gravitational pulls tearing at each other, preventing any stable, symmetrical structure from taking hold. They were works in progress, cosmic toddlers stumbling through a chaotic nursery. Yet within this apparent disorder, an incredible frenzy of creation was underway. These galaxies were stellar factories operating at maximum capacity, forging new stars at a rate that would put our own Milky Way to shame. While our galaxy might form 1 or 2 new stars each year, some of these ancient powerhouses were producing hundreds, even thousands of stars annually. This frantic pace of star birth is almost unimaginable. Picture a single galaxy, not much larger than a small cluster in our own sky, suddenly igniting with the brilliance of 1,000 supernovae, as vast, dense clouds of pristine gas collapsed all at once into a firestorm of new suns. This explosive period of star formation could not last forever. It was fueled by immense reservoirs of primordial gas, but that fuel was either rapidly consumed by the ravenous birth of stars or blown away by the powerful stellar winds and supernova explosions of the first short-lived stellar giants. The very violence of their creation sowed the seeds for their own maturity, eventually calming the chaos and allowing for the more settled, structured galaxies we recognize today. What cosmic trigger finally quieted this frantic age of fire? And why did the universe's fervor for creation slow to its current, more measured pace? Their chaotic brilliance was fueled by a recipe of remarkable simplicity. The earliest galaxies were composed almost entirely of just 2 elements, hydrogen and helium, the pristine raw materials forged in the furnace of the Big Bang itself. This chemical simplicity is what astronomers mean when they call these ancient systems metal poor. In the language of astronomy, any element heavier than helium is considered a metal. In our modern Milky Way, and even in our own bodies, we find a rich diversity of these cosmic metals, elements like carbon, oxygen, iron, and gold. But in the dawn galaxies, these heavier elements were almost entirely absent. They were cosmic kitchens, working with only the most basic ingredients. This purity had profound consequences. The first stars that formed from this primordial gas were fundamentally different. Without heavier elements to help cool the gas clouds and fragment them, these clouds could collapse into much larger, more massive stars. These stellar behemoths burned at ferociously high temperatures, lived for only a few million years, and then died in spectacular supernova explosions. It was within these violent deaths that the universe forged the first metals, seeding the surrounding gas with the ashes of those first stars. The next generation of stars then formed from this slightly enriched material, and with each stellar life cycle, the universe became gradually more chemically complex. So when we observe a distant, metal-poor galaxy, we are witnessing a universe still working with its original, unspoiled toolkit, a snapshot of cosmic chemistry in its most elementary form. How did that first sprinkle of stardust forever change the recipe for building everything that followed? This pristine simplicity, however, hid a monstrous secret at the heart of the chaos. We have discovered that some of these incredibly ancient galaxies already contained supermassive black holes in their cores, entities so vast they defy easy explanation. A supermassive black hole is a gravitational sinkhole with the mass of millions, even billions, of suns crushed into a point of infinite density. Finding such mature monsters in galaxies that were, by cosmic standards, just born, presents a profound puzzle. How could something so immense and complex form so quickly after the Big Bang? The evidence comes from quasars, the intensely bright beacons powered by these voracious black holes. We see quasars shining from an era when the universe was less than 1 billion years old, meaning the black holes driving them had to have grown to staggering sizes in an astonishingly short time. This suggests that the seeds for these cosmic giants were planted almost immediately, perhaps from the direct collapse of immense gas clouds or the remnants of the very first truly colossal stars. Their existence forces us to rewrite the story of how the largest structures in the universe came to be, compressing timelines we once thought were fixed. What cosmic conditions could possibly have allowed for such rapid and monstrous growth? The answer lies in the frenzied environment of the young cosmos itself. The early universe was a much denser and more crowded neighborhood, and this density fueled a constant state of violence through galactic mergers. Galaxies did not form in isolation. They were drawn together by gravity, colliding and merging in a slow-motion cosmic dance that was both destructive and creative. When two young galaxies smashed together, it was not like two solid objects crashing. It was more like two crowds of stars passing through one another, their intricate orbits thrown into utter disarray. But within those vast clouds of gas that filled each galaxy, the collision was transformative. The immense forces of the merger compressed the gas, triggering firestorms of new star formation on a scale we can scarcely reproduce today. These events were the ultimate stellar nurseries, lighting up the galaxies with a ferocious blue-white glow of countless newborn suns. At the very same time, this chaos fed the hidden beasts at their centers. The merging process funneled enormous amounts of gas and stars directly toward the central supermassive black holes of each galaxy. As this material spiraled inward, it formed a searingly hot, glowing disk of matter called an accretion disk, releasing a torrent of radiation that we observe as a brilliant quasar. So a single galactic merger did two things at once. It lit up the galaxy with a burst of new stars, and it turned on the central quasar, feeding the black hole and making it grow even larger. This symbiotic relationship between stellar birth and black hole growth was the engine that built the early universe. The most brilliant and massive galaxies we see from this era were likely the products of the most dramatic mergers, cosmic cities built from the rubble of countless collisions. Is it possible that our own peaceful Milky Way once shone with the furious light of a quasar, its central black hole feasting on the wreckage of a long-forgotten galactic union? But what if we could build a telescope more powerful than anything ever engineered? The universe, in its infinite ingenuity, provides exactly that through a phenomenon called gravitational lensing. It is a natural telescope, forged by gravity itself. The principle relies on Einstein's theory of general relativity, which tells us that mass warps the fabric of space and time. A massive object, like a galaxy cluster, acts like a lens in space, bending the light from objects lying far behind it. This cosmic mirage does two remarkable things. First, it can magnify the light of the distant background galaxy, making it appear dozens of times brighter than it really is. Second, it can distort and stretch the galaxy's image, often into long, faint arcs of light that curve around the foreground cluster. Without this natural assist, many of the most distant galaxies would simply be too faint for even our best telescopes to see. We are essentially using the gravity of one cosmic object as a magnifying glass to spy on another far more ancient one. This allows us to peer deeper into the cosmos and further back in time than would ever be possible with our own technology alone. It is as if the universe is handing us a key, using its own immense structures to illuminate the darkest chapters of its own history. What other faint whispers from the dawn of time might be revealed through these natural cosmic lenses? This process of clearing the cosmic fog is known as the Epoch of Reionization, a pivotal chapter in the story of our universe. For hundreds of millions of years, the cosmos was filled with a thick, neutral hydrogen gas, a fog that trapped light and kept the universe in a kind of twilight. Then the first sources of light began to switch on. The intense ultraviolet radiation from those earliest galaxies and quasars acted like a cosmic sunrise. Its energy so powerful, it began to strip electrons away from the atoms of that pervasive hydrogen gas. This transformation from neutral to ionized hydrogen is what we call reionization. It was not a gentle process, but a violent and fundamental change to the very fabric of intergalactic space. Think of it as a great thaw, where vast sheets of cosmic ice are slowly melted by the rising sun, eventually clearing the view to a crystal clear sky. This epoch was the universe's final transition from its opaque, formless infancy into the transparent, structured cosmos we observe today. How did the first flickers of starlight manage to illuminate the entirety of existence, and what guided this great transformation? The answer lies in the most brilliant beacons of the early universe, the quasars. A quasar is the intensely luminous core of a distant galaxy, powered by a supermassive black hole that is actively feeding. As vast amounts of gas spiral into the black hole, the material heats up to millions of degrees, glowing with a ferocious intensity that can outshine an entire galaxy of 1 trillion stars. Because they are so extraordinarily bright, quasars can be seen from the farthest reaches of space and time, acting as cosmic lighthouses whose beams pierce through the remaining patches of primordial fog. When astronomers study the light from these distant quasars, they can analyze its spectrum. They search for the specific dark lines created by the absorption of light by neutral hydrogen gas. By measuring how much of this absorption is present at different distances, they can effectively map the progress of reionization. A quasar's light is like a probe sent through the early universe, revealing where the fog was thick and where it had begun to clear. These brilliant beacons illuminate not only their own immediate surroundings, but also the entire era in which the universe became the transparent, star-filled expanse we call home. These brilliant cosmic lighthouses, the quasars, do more than just illuminate the early universe. They cast a light on a modern mystery so profound it threatens to upend our entire understanding of cosmic history. This is known as the Hubble tension. At its heart is a simple but critical question. How fast is the universe expanding right now? You would think we could agree on a single number, but we cannot. One method involves studying the local universe, using pulsating stars and specific types of supernovas as standard candles to measure distances and calculate a current expansion rate. This gives us one very precise answer. Another method looks back to the very beginning, to the afterglow of the Big Bang itself, the cosmic microwave background. By studying the subtle patterns in this ancient light, we can predict how the expansion should have evolved to the present day, yielding a different, equally precise answer. The problem is, these two numbers do not match. the local universe appears to be expanding faster than the early universe's data says it should be. This is not a small statistical fluke. It is a persistent and significant discrepancy that has withstood years of re-examination. It suggests a fundamental flaw in our standard model of cosmology, a model that has been spectacularly successful in every other way. So where do the most distant galaxies fit into this puzzle? They act as a crucial independent check, a third witness in this cosmic courtroom. By observing these ancient galaxies and their redshifts, we can trace the expansion history of the universe at intermediate epochs, filling in the timeline between the primordial afterglow and our local neighborhood. If the distant galaxies confirm the faster expansion rate seen locally, it would be powerful evidence that our understanding of the early universe, or perhaps the nature of dark energy itself, is incomplete. We may be on the verge of discovering that the force driving cosmic expansion is not constant, but changing in ways we never anticipated. The light from the earliest galaxies, therefore, carries a double message. It tells us about the universe's infancy, and it holds a key to understanding its unexpected and accelerating maturity. What if the universe's very first structures are the very thing that finally clarifies its ultimate fate? The brilliant light of ancient galaxies reveals an even deeper, invisible architecture shaping the cosmos. When astronomers study the rotation of these distant star cities, they encounter a puzzle. The stars at the outer edges of galaxies are moving far too quickly. According to the laws of gravity and the amount of visible matter we can see, these remote stars should be flung out into the void, yet they remain securely bound. The only explanation is that each galaxy is embedded within an enormous, massive halo of something we cannot see, a substance that does not emit, absorb, or reflect light. This is our most direct evidence for dark matter. Its immense gravitational grip is the invisible hand that holds fast-flying stars in their orbits, preventing galaxies from tearing themselves apart. This unseen scaffolding did more than just anchor individual galaxies. It orchestrated the entire large-scale structure of the early universe. The distribution of the first galaxies was not random. They huddled together in vast clusters and long, thread-like filaments, tracing out a pattern known as the cosmic web. This magnificent architecture was not built by the galaxies themselves. They were merely the glittering lights strung along a pre-existing framework woven from dark matter. Billions of years ago, slight ripples in the density of dark matter, imprinted in the first moments after the Big Bang, began to collapse under their own gravity. Ordinary matter, the hydrogen and helium gas, was then pulled by gravity into these growing dark matter wells. It was here, within these concentrated knots and filaments of the invisible web, that the first galaxies were born. So when we map the positions of the most distant galaxies, we are not just charting stars. We are drawing the ghostly blueprint of the universe itself, revealing the hidden skeleton upon which all visible reality is draped. How does an unseen force continue to guide the evolution of everything we see in the night sky? The death of a single star can illuminate the history of the cosmos. In a galaxy so distant we see it as it was over 10 billion years ago, astronomers witnessed the titanic explosion of a supernova. This was not just any stellar death. It was the most distant supernova ever confirmed, a cosmic cataclysm whose light had been traveling for more than 3/4 of the universe's current age. Its discovery was a monumental achievement, like spotting the flash of a single match lit on a mountain peak dozens of miles away. This ancient detonation is classified as a Type Ia supernova, a specific kind of explosion that occurs in binary star systems. What makes this type of supernova so special is its predictability. They all tend to explode with roughly the same intrinsic brightness, a known and consistent peak luminosity. This consistency makes them one of the most valuable tools in an astronomer's toolkit, known as standard candles. Think of it like knowing the exact wattage of a light bulb. If you know how bright it truly is, you can calculate its distance by measuring how dim it appears from your vantage point. By observing this most distant supernova and comparing its known brightness to its observed faintness, scientists can precisely measure the vast expanse to its host galaxy. This provides a critical, independent check on our cosmic distance ladder, helping to calibrate the expansion rate of the universe across immense spans of time. But this event is more than just a measuring stick. It is a fossilized record of stellar death from the universe's youth. The chemical elements forged in its fiery heart and blasted out into space tell us about the types of stars that were dying in that early epoch. This single, fleeting point of light offers a direct glimpse into the life cycle of the first generations of stars, revealing how the early universe seeded itself with the heavy elements necessary for planets and ultimately for life. These violent stellar deaths did more than just forge new elements. They fundamentally reshaped their own galactic homes. Within the brilliant cores of those ancient galaxies, a relentless cycle of creation and destruction was underway. Every time a massive star ended its life in a supernova, it did not fade away quietly. The explosion acted like a colossal piston, driving a shock wave that blasted through the surrounding clouds of gas. These were not gentle breezes, but hurricane-force tempests flowing out from the galaxy at speeds of millions of miles per hour. This is the phenomenon of galactic winds, a vital force in the life story of every galaxy. Imagine a vast forest where every time a giant tree falls, it unleashes a gale so powerful it scatters seeds and soil far and wide, clearing space for new growth, but also preventing the forest from becoming too dense. On a cosmic scale, these winds of supernova eject did something similar. They swept up enormous quantities of the very gas that fuels star formation and hurled it out of the galaxy entirely. This process, known as feedback, acts as a cosmic regulator. It is a self-imposed brake on a galaxy's own growth. Without it, a galaxy would consume its gas reservoir in a single, frantic burst of star formation, burning brilliantly but briefly before fading into a dim, stagnant system. But with galactic winds, the process is stretched out over billions of years. The furious pace of star birth is slowed, as the raw material for new stars is literally blown away, ensuring that star formation can continue at a more sustainable rate across cosmic time. The most dramatic feedback, however, comes from the supermassive black holes at the galaxy's heart. When a black hole is actively feeding, it can generate winds and jets of energy so powerful they can quench star formation across the entire galaxy. These outflows, driven by the intense radiation and magnetic fields around the black hole, can heat the galactic gas to such high temperatures that it can no longer collapse to form new stars. This effectively shuts down the galaxy's main engine of growth, leaving it to age passively. This incredible feedback loop, where the products of star formation and black hole activity themselves dictate the future pace of that formation, is a key to understanding why galaxies look the way they do today. And the material expelled by these winds does not simply vanish into nothingness. It is a vital contribution to the cosmos. The gas blown out of these early galaxies, now enriched with heavy elements from countless supernovae, is injected into the vast, empty spaces between galaxies. This process seeds the intergalactic medium with the building blocks for future generations of stars, planets, and life. The iron in your blood and the calcium in your bones were once part of such a galactic wind, expelled from an ancient star city and cast adrift on a cosmic current, eventually to find a new home in a fledgling solar system. How many times were the elements that form our world recycled through these violent galactic storms before they finally came to rest here? This cosmic recycling of elements created a new and unexpected challenge for astronomers, a veil of cosmic dust. As generations of stars lived and died, they not only forged heavy elements, but also spewed vast amounts of fine, sooty particles into the interstellar medium. This dust, composed of tiny grains of carbon and silicon compounds, acts like a fog throughout a galaxy. It does not simply block light, it transforms it. Shorter, bluer wavelengths of light are easily absorbed by these microscopic grains, while longer, redder wavelengths can pass through more easily. The effect is a phenomenon known as dust reddening, which makes a galaxy appear redder than it truly is. This creates a serious complication when trying to study the early universe. A galaxy might look extremely red and distant because of the cosmological redshift from the expansion of the universe, or it might just be a closer galaxy shrouded in a thick blanket of its own dust. Distinguishing between the two is critical for building an accurate map of cosmic evolution. For telescopes like Hubble, which primarily sees invisible light, this dust was an impenetrable curtain. Countless galaxies, especially those undergoing intense bursts of star formation, and therefore producing immense amounts of dust, were completely hidden from view. They were the universe's secret cities, glowing brightly but invisible to our most powerful eyes in the sky. How many of the earliest galactic building blocks were simply missing from our senses, lost behind the sooty smog of their own creation. The James Webb Space Telescope was specifically engineered to lift this veil. Its infrared vision sees the heat glow that this cosmic dust itself emits, and it can peer straight through the dusty clouds that block visible light. Where Hubble saw an empty patch of space, Webb often reveals a brilliant galaxy shining from behind the cosmic smog. It is like switching from a searchlight that is blinded by fog to a thermal sensor that sees the warm objects hidden within it. This capability is revolutionizing our count of early galaxies, revealing that the universe's first chapters were even more crowded and active than we ever suspected. These galactic building blocks were not the majestic spirals we know today. The true seeds of the first galaxies are thought to be proto-galaxies, small, dark matter clumps that acted as cosmic gathering points. Imagine these as the foundational bricks of a future city, invisible scaffolds where gravity could begin its slow, patient work. Within the gravitational wells of these dark matter halos, the first streams of pristine hydrogen and helium gas were captured. This was the raw construction material, and within these small, dense clumps, the very first stars ignited. A protogalaxy was likely a feeble thing, a small cluster of brilliant, massive stars shining in an overwhelming sea of darkness. They were the cosmic equivalents of tiny villages, destined to merge with their neighbors to form the first true towns and cities. Many of the faint, distant smears of light we observe with powerful telescopes are not giants, but their ancient diminutive ancestors. In fact, the most common type of galaxy in the universe, both then and now, is the dwarf galaxy. These are small, faint systems containing only a few billion stars, a mere fraction of the hundreds of billions found in a galaxy like our Milky Way. Because they are so intrinsically dim, we can only see the very closest dwarf galaxies in our local neighborhood. But when we look deep into the distant, early universe, our telescopes are sensitive enough to pick them out. What we are often seeing are the building blocks of our own cosmic home, the small villages that, through countless mergers over billions of years, assembled themselves into the grand metropolises we see today. Our entire Milky Way is surrounded by a swarm of dwarf galaxy satellites, the surviving remnants of this ancient construction phase. They are the living fossils of the cosmic dawn, offering us a direct window into the humble origins of all galactic structures. How many of these faint, primordial clumps did it take to build a single spiral galaxy like our own? The faint blueprints for all galactic majesty were drawn in the universe's first moment. The cosmic microwave background is the oldest light we can see, a snapshot of the cosmos when it was a mere 380,000 years old. This afterglow of the Big Bang appears as a nearly uniform glow across the entire sky, but it holds within it the faintest of imperfections, tiny variations in temperature, no larger than 1 part in 100,000. These minute ripples are the cosmic seeds from which everything we see eventually grew. They represent slight overdensities in the primordial soup, regions where there was just a little more matter than average. Over billions of years, gravity acted on these seeds, relentlessly pulling more and more material into these slight bumps. The densest knots in this cosmic fabric eventually collapsed to form the first protogalaxies and the vast dark matter scaffolding of the cosmic web. So when we point our telescopes at a galaxy 13 billion light-years away, we are not looking at a random object. We are witnessing the direct and magnificent consequence of one of those specific ancient temperature fluctuations. That galaxy is the mature, brilliant outcome of a tiny whisper of density from the dawn of time. How did a temperature difference smaller than 1,000th of a degree give rise to a city of 100 billion suns? The story of galaxy formation is simply the next chapter in the epic that began with the CMB, a tale of gravity's patient work transforming quantum seeds into a universe of light. The violent dance of galaxy mergers leaves behind cosmic signatures written in starlight. When two galaxies are drawn together by gravity, they do not simply crash. Instead, their immense gravitational fields pull and stretch each other, drawing out vast streams of gas and stars into long, graceful arcs that can span hundreds of thousands of light years. These are tidal tales, the visible scars of a galactic collision. In some of the deepest Hubble and Webb images, we can see these faint, ethereal bridges connecting distant, blurry galaxies, a frozen moment in a slow-motion ballet of destruction and creation. These tales are not just beautiful, they are fertile. The same gravitational forces that pull them apart also compress the gas within them, triggering the birth of new, brilliant blue star clusters that line the tidal streams like pearls on a cosmic necklace. This is the paradox of galactic violence. It simultaneously tears down old structures and seeds new ones. How many of the star clusters in our own Milky Way were born in such a chaotic encounter billions of years ago? The light from a distant galaxy is a composite message from billions of individual stars. By carefully dissecting this light into its full spectrum, astronomers can perform a kind of cosmic demography, determining the ages and types of the stellar populations that make up that faraway city. They look for specific absorption lines and overall color to understand the galaxy's history. A galaxy glowing with an intense blue light is a sign of vibrant youth, filled with hot, massive, short-lived stars that are burning ferociously. This indicates a recent, major episode of star formation. A galaxy that appears more reddish, on the other hand, is typically an older system. Its massive blue stars have long since died off in supernova, leaving behind the cooler, longer-lived red stars to dominate its glow. Many of the most distant galaxies show a surprising mix, a blue tint from frantic new star birth, superimposed on a redder background from an even earlier generation of stars. This tells us that star formation in the early universe happened in waves, with intense bursts followed by quieter periods. The light we capture in our telescopes is the combined voice of countless generations of stars, each telling a part of the story of their galactic home. Our cosmic census of the early universe is about to expand beyond all recognition. While the James Webb Space Telescope has opened a new window into the cosmic dawn, the next generation of observatories is already poised to push the frontier back to the very edge of time itself. These new instruments are not merely improvements, they are revolutionary leaps designed to answer the very questions Webb has just begun to ask. The Nancy Grace Roman Space Telescope, set to launch in the next few years, will act as a wide-angle lens to Webb's powerful magnifying glass. Where Webb stares intently at tiny, deep patches of sky, Roman will conduct vast panoramic surveys, mapping the cosmos with a speed and breadth that is almost unimaginable. It will find millions of high redshift galaxies, transforming our search from the discovery of individual celestial jewels to the mapping of entire continents of early structure. This statistical power will allow us to see the full tapestry of the early universe, understanding not just the rare, brilliant giants, but the countless faint building blocks that were the true foundation of cosmic evolution. But to peer into the absolute darkness before the first stars, we must look from the ground with a new kind of giant. The Extremely Large Telescope, or ELT, being built in the high deserts of Chile, will feature a primary mirror an astounding 39 meters across. That is nearly half the length of a soccer field, collecting more light than all of the largest existing optical telescopes combined. Its sheer size will grant it an unprecedented ability to dissect the faint infrared glow of the most distant objects. Where Webb identifies a faint red smudge as a candidate primordial galaxy, the ELT will be able to spread that same smudge out into a detailed spectrum, confirming its distance with absolute certainty and revealing the chemical composition of its stars and gas. Its immense resolving power might even allow it to see the internal structure within these infant galaxies, watching as the first star clusters and swirling disks begin to take shape. Together, this space and ground-based duo will push our vision into the universe's first 200 million years, a period known as the Cosmic Dark Ages that has so far remained entirely hidden from our view. This is the final frontier of observational cosmology, the era when the first proto-galaxies were just beginning to ignite. What will we find in that profound darkness? Will we see the solitary glow of the very first star, or the collective light of the very first city? The answers are waiting, just beyond our current sight, in the faint whispers of the cosmic dawn. These galactic giants are often swaddled in colossal clouds of glowing gas. Some of the most distant galaxies are found at the heart of immense structures known as Lyman alpha blobs. These are not galaxies themselves, but vast, nebulous clouds of hydrogen gas that can span hundreds of thousands of light years, dwarfing the galaxies within them. They glow with a specific wavelength of ultraviolet light, emitted by hydrogen atoms as they cool down. The sheer scale of these blobs is difficult to comprehend, each one a cosmic nebula so large it could engulf an entire group of galaxies like our own local group. What could possibly energize such a titanic structure, causing it to shine across the cosmos? The leading theories point to the incredible violence happening at their cores. Either a ferocious burst of star formation within the central galaxy is flooding the surrounding gas with ultraviolet radiation, or the intense glare from a feeding supermassive black hole is illuminating the cloud from within. These blobs are the visible aftermath of extreme cosmic energy, a temporary and brilliant halo of light cast by a galaxy in its most explosive phase of life. But even these glowing clouds are just the visible tracer of something far larger and more permanent. Every galaxy, from the smallest dwarf to the largest spiral, is embedded within a vast spherical halo of dark matter. This invisible cocoon is the true foundation of a galaxy, its immense gravitational pull acting as the anchor that holds the entire structure together. Without this dark matter halo, the galaxy's rapid rotation would fling its stars into the void. We cannot see this halo directly, but we can map its presence and shape by observing how it bends the light of more distant galaxies, an effect called gravitational lensing. These halos are not empty. They are also filled with the incredibly hot, thin gas that emits X-rays, a faint, seething atmosphere that surrounds the galaxy. This hot gas halo is a relic of the galaxy's formation, the final remnants of the primordial material that collapsed billions of years ago. So the galaxy we see in a telescope image is merely the bright, dense core of a much grander entity, a tiny, glittering jewel set within a vast, invisible sphere of dark matter and a shimmering, hot gaseous atmosphere. What we call a galaxy is only the most visible part of an immense and mostly hidden cosmic structure. Even the spin of a galaxy holds a story from the dawn of time. For the very first time, astronomers are not just seeing these ancient galaxies, they are measuring how they turn. The faint red smudges that represent the earliest star cities are now revealing subtle signs of rotation. This spin, this inherent angular momentum, is a fundamental property, a cosmic inheritance from the universe's birth. The prevailing theory suggests that this rotation was seeded in the first moments after the Big Bang, as tiny quantum fluctuations were stretched to cosmic proportions by a period of rapid inflation. These ripples in spacetime created a universe that was not perfectly smooth, but one filled with gentle swirls and currents in the fabric of the cosmos. As dark matter and gas collapsed under gravity to form the first protogalaxies, they preserved and amplified these primordial swirls, setting the entire structure into a slow, majestic spin. The very first galaxies likely rotated in a chaotic, disordered way, their motion a reflection of the turbulent environment from which they were born. But in some of the more mature infant galaxies we observe, a remarkable transition is already underway. We are witnessing the very birth of orderly rotation, the moment when chaos begins to settle into a stable disk. How does a formless cloud of gas and stars transform itself into a spinning pinwheel? It is a process governed by gravity and conservation of angular momentum, the same principle that causes a figure skater to spin faster as they pull their arms in. As a protogalactic cloud collapses, any small initial spin it possesses becomes magnified. The cloud naturally flattens into a disc shape, much like a chef spinning a ball of pizza dough, with the material settling into a plane of rotation. The incredible thing is that we can now detect this in galaxies observed just a few hundred million years after the Big Bang. By analyzing the faint light from opposite sides of a distant galaxy, astronomers can measure the Doppler shift. One side of the rotating disk will be moving slightly toward us, its light blue shifted, while the other side moves away, its light red shifted. This delicate measurement reveals not just that the galaxy is spinning, but how fast and how ordered that spin has become. These first measurements are revealing a surprising diversity. Some early galaxies are already well-ordered, fast-spinning disks, while others are still chaotic and turbulent, their rotation barely discernible from random motions. This tells us that the path from a chaotic clump to a graceful spiral was not a uniform one. Some galaxies achieved stability quickly, while others took much longer. The spin of a galaxy is more than just its motion. It is a fossilized record of the forces that shaped it, a direct link to the swirling currents of the infant cosmos. What does the specific spin of our own Milky Way tell us about its unique and violent origin story? The faint glow between galaxies tells a story of ancient violence. Within the first massive clusters of the early universe, a delicate light permeates the empty space, a phenomenon known as intracluster light. This is not the concentrated shine of a galaxy, but a ghostly, diffuse glow from countless stars that have been torn from their homes. These stars are the cosmic refugees of galactic collisions, their orbits shattered by the immense gravitational tides unleashed when early galaxies brushed past or merged with one another. Ripped from their parent galaxies, these stars were flung into the intergalactic void, forever doomed to wander the dark spaces between cities of light. This faint illumination is the permanent echo of those primordial encounters, a shimmering fossil of the chaos that built the cosmic web. How many suns now drift alone in that profound darkness, their light so faint it can only be seen when we combine the glow of millions. Orbiting these first large galaxies were their smaller companions, the satellite galaxies. These dwarf systems, held in the gravitational sway of a larger host, are the key to understanding galactic growth. The search for these faint satellites around distant, ancient galaxies is one of astronomy's greatest challenges, like trying to spot a firefly next to a brilliant searchlight from billions of light years away. Yet their existence is crucial. According to our models of cosmic structure, the dark matter halos of the first giant galaxies should have been swarmed by hundreds of these small satellite galaxies. They are the leftover building blocks, the small villages that were gravitationally captured, but not fully consumed by the growing metropolitan galaxy. Finding them confirms the bottom-up model of galaxy formation, where large structures are assembled from smaller ones. But there is a puzzle. In our local universe, we observe far fewer satellite galaxies around the Milky Way than our simulations predict. This is known as the missing satellites problem. Did many of these small galaxies fail to form stars and remain dark, or were they torn apart too early, their stars contributing to the intracluster light. By finding satellites around the earliest galaxies, we can see if this discrepancy exists at the dawn of time, or if it is a later development. Each captured dwarf galaxy is a testament to the hierarchical nature of the cosmos, a surviving piece of the original construction crew that built the universe we see today. To bridge the chasm between theory and observation, we turn to the digital universes born inside supercomputers. These are not simple animations, but fully realized virtual cosmos, governed by the precise laws of physics as we understand them. Scientists begin these simulations with initial conditions matching the early universe, a sea of dark matter and primordial gas, and then set the clock running forward over billions of virtual years. Gravity works its will, pulling matter into the filaments and knots of the cosmic web. Gas collapses, heats, and forms stars, which then explode, seeding space with heavy elements and driving powerful galactic winds. We can watch in accelerated time as tiny proto-galaxies merge and grow into the majestic spirals and ellipticals we see in our own neighborhood. The true power of these simulations lies in their predictive ability. When our telescopes, like Hubble and Webb, capture a faint red smudge of a distant galaxy, it presents a puzzle. Is it small and nearby, or massive and ancient? Is its strange shape the result of a recent collision? By comparing these real observations to the countless virtual galaxies generated in a simulation, astronomers can find a match. They can essentially ask the simulation, what specific series of events, what particular physics, could have led to a galaxy that looks exactly like this? This process allows them to reverse engineer the life story of that distant speck of light. Without these digital laboratories, the deep field images would be like finding a single mysterious fossil without any knowledge of the ecosystem it came from. The simulations provide the context, the entire ancient landscape, allowing us to understand not just what we are seeing, but the epic narrative of forces that created it. We are galactic archaeologists, sifting through the light of distant suns to uncover our own cosmic ancestry. By studying the most distant galaxies, we are not merely observing remote objects, we are excavating the deep past, digging through layers of cosmic time to understand how the universe built itself up from simple beginnings. Each ancient galaxy is a dig site, and its starlight is the artifact we analyze. The primary tool in this celestial excavation is the measurement of metallicity, the abundance of elements heavier than hydrogen and helium. In the earliest galaxies, we find this metallicity to be incredibly low, a sign of their youth and purity. As we look at galaxies from progressively later cosmic eras, we see this metallicity slowly rise, the cumulative result of billions of supernovae, polluting the interstellar gas with the ashes of dead stars. This is the fossil record of the universe, written not in stone, but in the elemental composition of suns. But the story becomes even more detailed when we look within a single, distant galaxy. Astronomers can now map the distribution of these heavy elements across a galaxy's disk, creating a chart of its metallicity gradient. Think of a newly founded city. The oldest, most established central districts are often the most built up, with the most infrastructure and the highest concentration of wealth and resources. In a similar way, the central core of a galaxy is typically where star formation began first and proceeded most vigorously. Countless generations of stars lived and died there, rapidly enriching the central gas with metals. As a result, The core of an ancient galaxy often shows a much higher metallicity than its outer suburbs. The stars forming in the outskirts are born from gas that is more pristine, less polluted by previous stellar generations. This gradient is a frozen timeline. By measuring how steep or shallow this metallicity slope is, we can read the galaxy's life story. A very steep gradient with a rich center and poor outskirts suggests the galaxy formed quickly and from the inside out. A shallower gradient might indicate a more turbulent history, perhaps shaped by a major merger that churned and mixed the galactic gas, homogenizing its chemical composition. So a single, faint smear of light from the early universe, when dissected with the right tools, can reveal not just its age and distance, but the precise sequence of events that assembled it, from its first central spark to its final, settled form. These primordial giants have never been directly seen, yet their existence is written into the very fabric of the cosmos. We call them population 3 stars, the legendary first generation forged from the pristine hydrogen and helium of the Big Bang. Their hypothetical nature is what makes them one of the last great holy grails of astronomy. Unlike the stars of today, which contain a sprinkling of heavier elements, population 3 stars were pure, untainted by the ashes of any previous stellar generation. This elemental purity is the key to their incredible and terrifying nature. Without heavier elements to help radiate heat away, the collapsing clouds of primordial gas could not fragment into small pieces. Instead, they collapsed into true behemoths, stars thought to be hundreds of times more massive than our own sun. Imagine a single star burning with the ferocious intensity of millions of our suns, a brilliant blue beacon shining in the universal darkness. Their lives were as spectacular as they were brief, burning through their nuclear fuel at a staggering rate. They lived for only a few million years before meeting a cataclysmic end. Their deaths were not ordinary supernova, but something far more violent, known as pair instability supernova. In these ultimate explosions, the entire star would be obliterated, completely annihilated without leaving behind a black hole or neutron star. They turned themselves into pure energy and scattered the first heavy elements across the cosmos. This is why finding even a single living population 3 star is so difficult. They all died young, billions of years ago. So where do we look for their ghosts? The answer lies in the most distant galaxies, the ones we see in their cosmic infancy. Astronomers are scouring the light from these ancient systems for a specific, telltale signature. Because population 3 stars were so hot, they would have emitted most of their light in the high-energy ultraviolet part of the spectrum. If a distant galaxy contained a significant cluster of these monsters, its light would carry a unique chemical fingerprint, a complete absence of the heavy elements that only later generations of stars would produce. The James Webb Space Telescope is our best hope for finally spotting this signature. It is searching for galaxies with a surprisingly strong infrared glow, but with a spectrum that is eerily clean, devoid of the familiar lines of oxygen, carbon, or silicon. Finding such an object would be like discovering a living dinosaur, a direct window into the universe's first and most powerful engines of creation. What would it mean to finally glimpse the light of a star whose death made our own existence possible? At the hearts of these ancient stellar cities raged engines of unimaginable power, known as active galactic nuclei. And a GN is not the galaxy itself, but its intensely luminous core, a beacon so brilliant it can outshine the billions of surrounding stars combined. This phenomenal energy output comes from a supermassive black hole in the process of feasting. As colossal amounts of gas, dust, and even stars spiral into the black hole's gravitational grip, they do not fall in directly. Instead, they form a searingly hot, swirling disk of doomed matter called an accretion disk. Friction within this disk heats it to millions of degrees, causing it to glow across the entire electromagnetic spectrum, from radio waves to X-rays. In some cases, the black hole's powerful magnetic fields funnel some of the infalling material into two jets that shoot out from the poles at nearly the speed of light, stretching for millions of light years into intergalactic space. When one of these jets is pointed almost directly at Earth, we see an especially bright and variable, a GN called a blazar. These distant active nuclei are more than just cosmic monsters. They are fundamental regulators of galactic evolution. The immense energy they release can heat the surrounding gas, preventing it from cooling and forming new stars, effectively quenching the growth of their host galaxy. The most distant quasars we observe are the GN of ancient galaxies, shining from a time when the universe was less than 1 billion years old, their existence challenging our understanding of how black holes could grow so massive so quickly. Their light, traveling for billions of years, carries the signature of this ferocious activity, a testament to the violent processes that shaped the cosmos from its very beginning. Yet even the sustained fury of an active galactic nucleus can be momentarily eclipsed by a single cataclysmic event from the far reaches of space. In a fraction of a second, a gamma-ray burst can release more energy than our Sun will emit in its entire 10 billion-year lifetime. These are the most powerful explosions known to exist since the Big Bang itself. They are brief, fleeting flashes of the highest energy gamma-ray radiation, often lasting only from a few milliseconds to a few minutes. The longest bursts, those lasting more than 2 seconds, are thought to be caused by the death of a rapidly spinning, massive star in a distant galaxy. As the star's core collapses to form a black hole, it launches ultra-relativistic jets that drill their way out through the star's outer layers. If one of these narrow, focused jets is aligned with Earth, we detect the resulting intense flash of gamma rays as a brilliant but fleeting cosmic beacon. The shortest bursts are believed to originate from the merger of two ultra-dense stellar corpses, like neutron stars. These events are so incredibly luminous that for a brief moment they can outshine every other gamma-ray source in the universe combined, including the active galactic nuclei. But their utility to astronomers extends far beyond their raw power. Because they are so bright, we can detect them from the farthest conceivable distances, from galaxies at the very edge of the observable universe. The light from these bursts journeys across the cosmos, and on its way, it passes through countless clouds of intergalactic gas. Each cloud imprints its own unique chemical fingerprint onto the burst's light, allowing scientists to dissect its spectrum and take a census of the material that lies between us and the explosion. A single random flash of light from a dying star billions of light years away thus becomes a powerful probe, illuminating the vast, dark web of the universe and revealing its composition and structure. What other secrets might be hidden in the brief, brilliant deaths of the universe's most massive stars? The very fabric of galactic neighborhoods has been transformed over cosmic time. Look at a modern galaxy cluster, a dense metropolis of galaxies, and you will find it dominated by red and dead ellipticals, vast cities of aging stars where new suns are rarely born. But peer back billions of years, and the scene changes dramatically. This is the Butcher-Oemler effect, a discovery that revealed how the past was a far more vibrant and chaotic place. In distant clusters, astronomers observed a surprising abundance of blue spiral galaxies, their azure hue a telltale sign of frantic star formation. These clusters were not the quiet retirement homes we see today, but bustling, active construction sites. The effect paints a clear picture of environmental evolution. A galaxy's fate is not sealed by its birth alone, but is profoundly shaped by the company it keeps. As a spiral galaxy falls into a dense cluster, it undergoes a harrowing journey. It first encounters the cluster's vast halo of searingly hot gas, a plasma that acts like a cosmic wind, violently stripping away the galaxy's own cool gas reservoir, the very fuel for new stars. This process, known as ram pressure stripping, can leave a galaxy barren in a single, dramatic pass. At the same time, the relentless gravitational tides from nearby galaxies pull and distort the spiral, disrupting its delicate structure in a process called galaxy harassment. These combined forces effectively strangle the galaxy, cutting off its star formation and causing its brilliant blue stars to age out and die, leaving behind the passive red glow of elderly stellar populations. The Butcher-Oemler effect is the statistical evidence of this universal transformation, showing us that the quiet, red clusters of today are the direct descendants of the blue, tumultuous cities of the early universe. What does this tell us about the ultimate fate of our own Milky Way as it continues its own long fall toward the immense Virgo cluster? The universe's largest cities were built on a foundation of cosmic consumption. Galactic cannibalism describes the process where a massive galaxy grows not just by merging with equals, but by devouring its smaller, orbiting satellite galaxies. This was the dominant method of growth in the crowded, chaotic early universe. A large galaxy's immense gravitational pull acts like an invisible net, slowly dragging a smaller companion closer over billions of years. The smaller galaxy is then tidally shredded, its stars stripped away and incorporated into the halo of the larger one, creating vast, faint streams of stars that are the galactic equivalent of archaeological ruins. Our own Milky Way is a cannibal, currently in the process of tearing apart and absorbing several dwarf galaxies, and bearing the scars of past meals in its outer stellar halo. This relentless consumption is how galaxies grew from the small, faint building blocks of the cosmic dawn into the majestic giants we see today. Yet, not all survivors of this violent era are bright and dense. Some are cosmic phantoms, galaxies that have escaped digestion only to wander as ghosts. These are the ultra-diffuse galaxies, or UDGS. They are as large as the Milky Way in terms of physical size, but they contain so few stars that they are incredibly faint, almost transparent. If you were to place one between us and a bright background galaxy, you might see the distant galaxy shining right through its ghostly disk. Finding these faint objects at significant distances is incredibly difficult, like trying to spot a wisp of smoke in the darkness from miles away. Their existence poses a fascinating puzzle. How did these vast, sprawling collections of gas and dark matter manage to form so few stars? Were they born in environments where their gas was stripped away early? Or do they possess some internal mechanism that suppressed star formation, leaving them as ethereal, dormant giants? These faint ghosts are a reminder that the early universe contained a far greater diversity of galactic structures than we ever imagined, each with its own unique and quiet story of survival. Even the quietest echo of the Big Bang can be disturbed. The cosmic microwave background, that ancient afterglow, is not completely uniform. Its journey across the cosmos is sometimes interrupted, and that interruption becomes a tool for discovery. This is the Sunyaev-Zeldovich effect, a subtle but powerful phenomenon. As the faint light of the CMB travels for billions of years, it occasionally passes through a massive galaxy cluster. These clusters are not just collections of galaxies. They are also filled with a superheated gas, a plasma with temperatures of millions of degrees. When the CMB photons, which are themselves a form of radiation, pass through this searing cloud, they receive an energy boost. A small fraction of these ancient photons collide with the high-energy electrons in the hot gas. During these collisions, the photons gain a little bit of energy, which effectively pushes them to a slightly higher frequency on the electromagnetic spectrum. It is like the light is being given a gentle nudge. The result is a specific, telltale distortion in the CMB's signature at the location of that cluster. From our point of view, the CMB appears slightly fainter at its characteristic wavelength and slightly brighter at a higher wavelength. This creates a unique cold spot on our maps of the microwave sky, a shadow that points directly to the presence of a massive cluster. The true power of this effect is its independence from distance. Unlike methods that rely on a galaxy's brightness fading with distance, the Sunyaev-Zeldovich effect does not diminish. Whether a cluster is relatively nearby or at the very edge of the observable universe, the distortion it imprints on the CMB is equally detectable. This allows astronomers to create a pure mass map of the universe, finding the most massive structures regardless of how faint their starlight has become. It is a way of seeing with gravity itself, using the universe's oldest light to illuminate its largest structures. What other invisible giants might be revealed by the shadows they cast upon creation's first light? The universe's most violent events broadcast their news in more ways than light. Beyond the brilliant quasars and gamma-ray bursts, there are messengers so subtle they can travel across the cosmos without being deflected or absorbed. These are cosmic rays, atomic nuclei accelerated to nearly the speed of light, and neutrinos, ghostly particles that barely interact with matter. Together, they offer a radically different window into the distant universe, one that could reveal processes hidden from even the most powerful telescopes. There exists a theoretical limit, known as the Greisen-Zatseping-Kuzmin cutoff, which predicts that the most energetic cosmic rays from distant sources should not reach Earth. The reason is a cosmic roadblock. As an ultra-high energy proton travels for billions of years through space, it inevitably collides with the photons of the cosmic microwave background, the leftover glow from the Big Bang. These collisions sap the proton's energy, preventing particles above a certain extreme energy from arriving from very far away. This cutoff is not just a curiosity, it is a fundamental feature of our universe's structure. Yet when we build detectors that scan the skies for these rare, high-energy particles, we sometimes find events that seem to defy this limit. We detect cosmic rays with energies so immense they appear to have come from beyond the local universe, suggesting they originated in cataclysms of almost unimaginable power. This presents a profound mystery. Either our understanding of the Gizike cutoff is incomplete, or there are sources of cosmic, rays so incredibly violent and nearby that they can overcome this universal speed limit. What cosmic accelerators could possibly hurl matter with such ferocious force? The suspects are the usual titans of the early universe, active galactic nuclei with their relativistic jets, or perhaps the mergers of supermassive black holes. But cosmic rays are not the only silent messengers. Neutrinos provide an even more direct, though incredibly difficult to capture, signal. These particles are so elusive that trillions pass through your body every second without a single interaction. They are born in the hearts of supernova, in the accretion disks of black holes, and in the violent engines of gamma-ray bursts. Because they are electrically neutral and barely have any mass, they travel in perfectly straight lines from their source, unaffected by magnetic fields or intervening matter. A neutrino detected from a distant galaxy would be a pristine telegram, an unaltered witness to the event that created it. While our current detectors are not yet sensitive enough to pinpoint neutrinos from specific ancient galaxies, the next generation of observatories aims to do just that. By combining the information from light, cosmic rays, and neutrinos, we could one day achieve true multi-messenger astronomy. We could see a distant galaxy in visible light, watch its central black hole flare up in gamma rays, and simultaneously detect a burst of neutrinos and a shower of cosmic rays from the same event. This would give us a complete, multi-sensory picture of the most extreme physics in the cosmos, revealing the inner workings of the universe's most powerful engines in a way that light alone never could. What hidden chapters of cosmic history are written in these silent, invisible signals, waiting for us to learn how to read them? This observational gap is known as the redshift desert, a frustrating void in our cosmic map. As the universe expands, it not only stretches a galaxy's light toward the red, but also shifts its entire spectrum of chemical fingerprints. For many telescopes, especially those like Hubble that excel in visible light, there is a specific range of distances where a galaxy's most important spectral lines fall into an observational blind spot. The most crucial of these lines is the Lyman alpha line, a strong ultraviolet emission from hydrogen gas that is a primary tool for confirming a galaxy's distance. For galaxies with a redshift between about 1.5 and 3, this vital line is shifted out of the visible range and into the near-infrared, a region where Hubble's vision grows dim and inefficient. It is as if these galaxies are speaking in a frequency our most powerful ears are barely able to hear. This creates a desert in our data, a span of billions of years in cosmic history where galaxies become exceptionally difficult to find and confirm. We know this era was critically important, a time when galaxies were rapidly maturing, building their bulges, and reaching peak star formation. Yet because of this spectral shift, our census of the universe during this vibrant adolescence remains incomplete. How did the universe transition from the chaotic building blocks of the early cosmos to the more settled galaxies we see later on? The answers are hiding in the quiet of the desert, waiting for a telescope that can listen to their faint, reddened whispers. There is a fundamental horizon beyond which no telescope can ever see. This ultimate barrier is not a limitation of our technology, but a frontier written into the history of the cosmos itself, a moment before the first galaxies even existed. We call this theoretical boundary the redshift wall. Imagine a time so early that the universe was still a smooth, dark soup of hydrogen and helium gas. The slight ripples from the Big Bang had not yet had time to collapse under their own gravity. In this primordial darkness, there were no stars, no quasars, no brilliant beacons of any kind. There was nothing to see because the objects we call galaxies had not yet been assembled. The light from that era is not faint, it is non-existent. The redshift wall represents the maximum distance, the maximum look-back time, beyond which the universe was simply too young and too smooth to form the structures we are trying to observe. We are not just looking for fainter and fainter objects, we are approaching the edge of time, the moment of first light. So where is this wall? Current theories and the most recent observations from the James Webb Space Telescope suggest we may be frighteningly close to it. We are already finding galaxies like GNZ 11, which we see when the universe was only 400 million years old. The wall might lie just beyond, perhaps when the universe was only 200 million years old, or even less. Peering beyond this wall requires a completely different kind of observation, one that does not rely on starlight at all. To witness the true birth of galaxies, we must learn to see the dark. The next generation of observatories will not look for the glittering cities, but for the faint blueprints of their foundations. They will target the cold hydrogen gas itself, the raw material of creation, before it ever collapsed into a star. How do you see an invisible cloud of gas in the void of space? The key is a specific wavelength of radio light emitted by neutral hydrogen, known as the 21 centimeter line. As the universe expands, this signal from the cosmic dark ages is stretched to meters or even kilometers in wavelength, becoming a faint radio whisper. Enormous, ambitious projects are being designed to listen for this whisper. Imagine a radio telescope not as a single dish, but as a vast field of simple antennas spread across a desert or even on the far side of the moon, a location blissfully free of Earth's radio interference. These instruments, like the proposed Lunar Crater Radio Telescope, would be tuned to the ultra-long wavelengths stretched by 13 billion years of cosmic expansion. Their goal is not to take a picture, but to create a map of the faint ripples in the primordial hydrogen gas. They would show us the cosmic seeds in the process of collapsing, the ghostly outlines of the very first proto-galaxies as they began to pull themselves together from the darkness. This would be the ultimate archaeological dig, revealing the universe not in its infancy, but in its womb. What will we learn when we finally gaze upon the empty canvas just before the first brushstroke of light? Every story of a distant galaxy is also a chapter in our own. We observe these ancient star cities from our home, the Milky Way, a grand spiral galaxy spinning in a quiet, nondescript corner of the cosmos. From our vantage point, we are not merely spectators. We are participants in the same grand evolutionary saga. Our galaxy, with its elegant arms and brilliant central bulge, is the product of the same violent and creative processes we witness in the deep past. It too was forged in the chaotic mergers of smaller proto-galaxies, its central black hole grown from a tiny seed over billions of years, its disk shaped by countless gravitational encounters. When we train our telescopes on a galaxy like GNZ 11, we are not just looking at a remote fossil. We are looking at a version of our own galaxy in its tumultuous infancy. That faint smudge of ancient light represents a phase our own Milky Way passed through long ago, a period of frantic star birth and chaotic growth. This cosmic perspective is profoundly humbling. The same elements that course through our veins, the iron and oxygen that sustain us, were first forged in the hearts of stars that lived and died in galaxies, just like those we see at the edge of time. Our solar system, our planet, and we ourselves are the late-born products of this 13 billion-year chain of stellar life and death, a chain that began in those first brilliant cities of stars. To study the most distant galaxies is to finally read our own galactic autobiography, written in the faint light of our cosmic ancestors. What new chapter will our own galaxy write in the eons to come? Our most powerful telescopes are the closest things we have to a true time machine. With every observation of a distant galaxy, we are not just looking across space, we are receiving a direct message from the universe's infancy, a priceless fragment of its memory. This ancient light is our only tangible connection to that formative era, carrying within its faint waves the story of how the first structures assembled, how the first elements were forged, and how the cosmic stage was set for everything that followed, including us. We are not passive observers of a static sky. We are active archaeologists of time, sifting through these delayed photons to reconstruct our own deepest history. The iron in our blood, the calcium in our bones, every atom that makes up our world was once part of such a distant, ancient star. By decoding the light from galaxies like GNZ 11, we are ultimately reading our own cosmic autobiography, a story that began in the brilliant, chaotic fires of the first star cities. What greater secret could these ancient messengers hold than the very recipe of our existence? This entire journey reveals a universe far more dynamic and mysterious than we ever dreamed. From the first flickers of starlight that burned away the cosmic fog to the supermassive black holes that grew to impossible sizes in a cosmic heartbeat, every discovery has rewritten a chapter of our cosmic story. We have watched as infant galaxies, chaotic and misshapen, defied our expectations with their brilliant maturity, forcing us to reconsider the very timeline of creation. We have traced the invisible architecture of dark matter that sculpted the cosmic web and felt the ghostly presence of the first stellar giants, whose violent deaths seeded the universe with the elements of life. This is not just a collection of facts, it is a living, breathing history of everything, a narrative pieced together from ancient light and gravitational whispers. The study of the most distant galaxies has fundamentally reshaped our understanding of cosmic evolution, proving that the universe's infancy was a period of explosive, efficient, and often violent creativity that set the stage for everything we see today. We have now reached the end of our 50 facts, but this is only the beginning of the conversation. I want to hear from you. Which of these cosmic revelations amazed you the most? Was it the ghostly blueprint of dark matter, the ancient galactic collisions, or the profound mystery of the redshift wall? Share your favorite fact in the comments below, and if you are hungry for more deep space mysteries, be sure to subscribe so you do not miss our next journey to the edge of understanding.